तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last few lectures we have been discussing about the metal oxide semiconductor junction or capacitor. We shall continue this discussion in this lecture. Let me remind you that our goal of these discussions on this topic is to explain the CV characteristics shown on this slide. We are coming closer to this explanation. As a first step, we said that we will explain the charge conditions in the MOS capacitor as a function of the DC applied voltage, and from there we will derive the CV characteristics. In the last class, what we explained was the following. In a MOS capacitor, when your voltage is greater than 0, you have depletion and inversion conditions, and we discussed these conditions in detail and said the following. When you increase the voltage from 0, first the depletion region starts expanding. The charge in the semiconductor required to sustain this high voltage, sustain this applied voltage, comes from the depletion region, okay, because of ionized impurity atoms. Now this proceeds until you reach the threshold. Beyond threshold, what happens is this depletion region stops expanding, and instead you have mobile electrons being attracted to the surface in large numbers. And beyond threshold, it is this mobile electron concentration or inversion layer charge concentration that goes on increasing, and the depletion layer concentration saturates. Now this was shown on a graph like this. So here the depletion charge is saturating and the inversion charge Qi is rapidly expanding beyond the threshold point. We also said that if you look at the voltages psi ox and psi s, that is the potential drop across oxide and silicon, as two components of the applied voltage, then when you increase the voltage from 0, psi ox keeps monotonically increasing. Now psi s also increases in the beginning, but beyond threshold voltage, when the depletion layer almost saturates, the psi s also saturates. So this is what we said about psi s, the surface potential. Beyond threshold, it saturates to a value phi t, okay. The saturation is approximate, of course, whereas the psi ox keeps increasing continuously because the silicon charge as a whole, which is sum of the inversion charge and the depletion charge, that keeps increasing, though the depletion charge saturates beyond threshold. Now we also derived an expression for Vt and as well as this phi t. Now this expression was Vt equal to square root 2q Na epsilon s phi t by C naught, which is oxide capacitance, plus phi t. This is the psi ox and this is psi s at inversion. we must remember two numerical values for any calculation related to MOS capacitors. One is the oxide capacitance for 0.1 micron oxide thickness, which is about 35.5 nanofarad per centimeter square, and the phi t is approximately 0.7 volts. It would be useful to remember these two values. Now in this lecture we would like to derive expressions for Qd as a function of voltage and Qi as a function of voltage. That is our first exercise in this lecture. Now before we take that up, let me explain one doubt that students often get. That is, how is it that the psi s almost saturates when your inversion charge is increasing? That is, the doubt is, when you increase the voltage beyond threshold, this electron concentration is going on increasing. So Ns is going on increasing. Now if Ns is going on increasing, how can psi s be constant? You know that we had said that psi s and Ns are related by the Boltzmann relation. Psi s is equal to Vt ln Ns by N naught. That is, if you look at this diagram, psi s is given by the ratio of this surface concentration to N naught and logarithm of this ratio multiplied by the threshold voltage. So if Ns increases, psi s should also increase, but we are saying psi s is almost becoming constant. How is this possible? Well, what we are saying is the following, that psi s depends logarithmically on Ns. So even if Ns increases, the increase in psi s will be very, very small, because Ns is logarithmic function of the psi s is logarithmic function of Ns. On the other hand, if you look at the inversion charge Qi, it increases almost linearly with Ns. The function is not exactly linear, but approximately we can say, if that function of this function psi s of Ns is logarithmic, this is almost linear. Qi is linear function of this Ns. So when Ns increases, Qi increases directly with Ns, whereas psi s increases logarithmically with Ns. That is why even though the inversion charge increases rapidly, the surface potential increases very slowly, and therefore we are treating it as a constant. Now let us return to our discussion related to derivation of equations for Qd and Qi. Now the starting point for this is the same as that we used for deriving this threshold voltage expression. So we can write V is equal to psi ox plus psi s. Psi ox is given by minus the silicon charge by the oxide capacitance. This is from the field picture. Okay, please note that Qs by C naught with a minus sign, because when the applied voltage is positive, the charge in the silicon is negative. Charge in the silicon is of opposite polarity to the voltage applied to the gate. That is why you have minus. So this is generally true. Now depletion as well as inversion. So in the expression for Qs, you will have Qd as well as Qi. Look at this graph. We said the Q silicon charge is obtained by summing up Qi and Qd. So let us understand this with the help of a field versus distance diagram. Now, so we draw the E versus X, okay, in the oxide and semiconductor. So at threshold, suppose this is the field distribution, so this is 4. In our nomenclature. Now beyond threshold, what happens is that you have a step in the electric field here, because you have an inversion charge which is almost like a sheet, and then your oxide electric field will be 3 times this electric field. So this in inversion, this step is Qi by epsilon s with a modulus, or you can put a negative sign because the charge is negative. This is by Gauss's law. So the inversion charge contributes to a step in the electric field. So we can draw the charge picture here underneath. This is the depletion charge under depletion approximation, and this is the inversion charge. We are not showing the charge in the metal, this is always positive whenever this charge is negative. So corresponding to this sheet charge, you have this step. This, on the other hand, this distance is minus Qd by epsilon s. So this total thing is Qs by epsilon s with a negative sign, silicon charge by epsilon s. As you go on increasing your voltage, since depletion layer does not expand beyond threshold, so we are talking of V greater than or equal to threshold. Because the depletion width does not expand, this triangle will almost remain the same, whereas this step will appear here and this will go on increasing as your V increases beyond Vt. But now what we are interested in is what is the oxide and the silicon drop. The oxide drop is given by this shaded area. So what you find is this electric field is nothing but this electric field into epsilon s by epsilon ox, okay, because you are shifting from silicon to silicon dioxide. So this value is minus Qs into minus Qs by epsilon s into epsilon s by epsilon ox, which is nothing but Qs by epsilon ox, and this area therefore is Qs by epsilon ox into T naught, because T naught is this width. Now this is how we have derived the threshold voltage expression also, okay. So that is the same thing. What we want to show here is that even when inversion charge is present, okay, the relation for the oxide potential drop is the same. So this is nothing but minus Qs by C naught. So if we show this potential on potential variation with X diagram, this is how it will be. So in depletion, suppose this is your potential at threshold, let us draw this to scale. For the particular calculation we did, we found that this is about 0.7 potential drop, whereas the remaining one is about 3.2. So which means this is almost 4.5 times this. So this is approximately to scale. This is your psi s and this is psi ox. This is 4, that is at threshold. this psi s will be phi t. That is, this area is phi t. So that is a link between this diagram and this diagram and this diagram. Okay. So from charge you get the electric field by Gauss's law, and by integrating the electric field or taking the areas in the electric field you get the potential versus x. This psi ox is this area, and that is minus qs by c naught. Now in inversion what will happen is this part will almost remain the same, only your oxide potential drop is going to change. Okay, this is what will happen. Now coming back to the equation here, therefore your conditions are psi ox is equal to minus qs by c naught, where qs is qd plus qi. In depletion qs is approximately equal to qd, whereas in inversion qs is equal to the value of qd at inversion plus qi. Now starting from here, these two equations, and substituting this into this and then this back into this, we can get the charge versus voltage relation. First let us take the depletion region QV relationship. So we can write V is equal to minus QD by C naught plus psi s. Now we want QD as a function of V. So to do that we must express psi s also as a function of QD. Now if you recall, when we wrote down the threshold voltage expression, okay, we wrote down the depletion charge at threshold as follows: QD is equal to minus of square root 2q epsilon s Na into phi t. This was at inversion. Please look into the derivation. Okay. So basically this derivation is related to this. So we must relate this area QD and this electric field here, and then this electric field is related to the area under this, which is the potential psi s. Okay. So following the same approach, if you try to derive the QD as a function of psi s, all that we need to do is replace phi t by psi s, and here this is in general valid until threshold, okay, which is in the depletion region. So once you know this, you know that psi s is given by QD square by 2q epsilon s Na by squaring both sides. So we can substitute this here and you will get an equation between V and QD. So this is a quadratic equation. So your relation is V is equal to minus QD by C naught plus QD square by 2q epsilon s Na. This is the equation for depletion region. Okay. Now how do you know that this equation is valid? Well, it depends on what is your value of psi s or V. So depletion region means V less than or equal to Vt but greater than or equal to 0, or psi s is less than or equal to phi t greater than or equal to 0. Let us write this here. that is the depletion. Now similarly, let us take the inversion condition. What is the charge voltage relation under inversion? Now incidentally, this quadratic equation represents this particular curve. Okay, please note how do we get this shape from here. The first term is a linear term, okay, and then the second term is a quadratic term, basically subtracting from the first term if you take the brackets. So in brackets if you write, you can write this as follows. So now this whole quantity will be on the negative axis, okay. So a linear term increasing, but then you have a quadratic term subtracting from the linear term. So that is what is seen here. So you have a linear term, a linear increase, but then since the quadratic term is there and subtracting, the magnitude goes on falling, and that is how you get this kind of shape. Okay, now let us return to the inversion charge. So in inversion, we can write V is equal to Qd inversion plus Qi with a negative sign upon C naught plus phi t, because inversion is characterized by V greater than or equal to Vt or psi s equal to phi t. So we must replace psi s by phi t, which we can write as minus Qi by C naught plus minus Qd inversion by C naught plus phi t. Now this sum is nothing but threshold voltage Vt. Therefore, you write this as V minus Vt is equal to minus Qi by C naught, or transforming this equation you get Qi is equal to minus C naught into V minus Vt. So you see Qi is linearly increasing with voltage, but please note this formula is only valid for V greater than Vt. So one must not say that if V less than Vt, Qi will be positive. There is no positive Qi for V less than Vt. This formula itself is valid only for V greater than Vt. Okay. In other words, now you can see that this particular shape is a straight line starting from Vt. Okay. That is the shape here. That is the shape for Qi. So what we derive is that the inversion charge increases linearly with the difference between the applied voltage and the threshold voltage. Now with this we have completed the QV characteristics of an ideal MOS capacitor. So let us summarize what we have obtained so far. So this is the Q versus V curve. The various segments, the equations are as follows. For this accumulation segment, that is this segment here, you can write Qa is equal to minus C naught into V, that is this segment. Then for the depletion segment, that is between 0 and Vt, you can write V is equal to minus Qd by C naught plus Qd square by 2q epsilon s Na. Now for this particular depletion charge segment beyond threshold this value is minus Qd inverse, and what is this? So Qd is equal to Qd inverse, which is nothing but minus of 2q epsilon s Na into phi t, where phi t is equal to 2 times Vt ln Na by Ni. Then you have the inversion segment, that is this inversion charge segment, and for this segment your equation is Qi is equal to minus C naught into V minus Vt. The threshold voltage expression Vt is given by minus Qd inverse by C naught, which is oxide potential drop, that is square root 2q epsilon s Na into phi t upon C naught plus the silicon drop, that is phi t. So these are the results for an ideal MOS capacitor. Okay. Now we must see what happens when the capacitor is not ideal or it is real. Now as we explained, in a real capacitor the extra things that we must take into account are, firstly, this metal or polysilicon gate and semiconductor, between them there is a contact potential which we have not taken into account, and also in addition you have a number of charges in oxide as well as at the interface. So the charges we listed were QIT, that is interface trapped charge, QOT, that is oxide trapped charge, QF, that is a charge at the interface, fixed charge at the interface, and QM, that is a mobile charge in oxide. Now we will not discuss the origin of all these charges, that is beyond the scope of our present work. So we will concentrate on the charge QF alone, effect of QF. Now it turns out that at silicon dioxide interface you have a positive charge which is said to be fixed because the value of this charge does not change with voltage. It is always present whenever you create a silicon dioxide interface. So right here at the interface you have this charge. Okay. Usually this charge is shown in a box because this is a fixed charge, it cannot move nor can it vary with voltage. Now very briefly, the origin of this QF is as follows. The chemical composition of the oxide layer or silicon dioxide layer is SiO2. Okay, so this is SiO2, whereas this is Si. Now you cannot have an abrupt transition from Si to SiO2, okay, in practice. So what is going to happen is that if you look at this interface in detail, so let us expand this interface. So on this side you have silicon and on this side you have silicon dioxide. So there will be a region in which the composition will gradually change from Si to SiO2. So here it is SiO2 and in this region it is SiOX, where X varies from 0 to 2. So here it is 0, X is 0 and here it is 2. So there is this layer, transition layer. Now because you do not have two oxygen atoms for one silicon, okay, so all the silicon atoms are not satisfied by bonding and therefore there is a charge that is created, a positive charge that is created, okay, and this positive charge is the charge that is called QF. So in our non-ideal MOS capacitor, which is the next topic that we will discuss, we will try to take into account the effect of QF and what is called the contact potential, or as we show that contact potential is nothing but work function difference, denoted phi ms. This is called work function difference. Now the question is, how do we take both of these into account? Let us start with the effect of QF. What effect will QF have? Now you can see that this positive charge QF will tend to find negative charge here, okay, in the nearest silicon substrate. So what does this mean? This means that if you have a p-type substrate here, then even when you don't apply any voltage, because of this fixed charge, you will already have a depletion layer. So you have charge in silicon even when there is no applied voltage. Recall that in ideal MOS capacitor, for no applied voltage there was no charge in silicon, whereas here you have a negative charge. Now if the QF is very large, you can even have inversion charge here in addition to depletion charge. So if you want to create the condition of zero charge in silicon, what you will have to do is, you will have to apply a voltage to the gate, so that these charges, instead of terminating on this side with an electric field like this, they terminate on the gate with an electric field directed in the opposite way. So you need an electric field like this, so that these positive charges will not look for negative charges in silicon. In other words, you have to put a negative charge equal in magnitude to the positive charge in the gate. So which means you must apply a negative voltage to the gate to create zero charge in silicon. Now zero charge in silicon, we said, corresponds to flat band conditions in semiconductor, if the semiconductor is uniformly doped, because then the conduction and valence bands are constant with distance when there is no charge. So therefore what we can say is that to create flat band conditions in silicon, you will have to apply a voltage in a non-ideal MOS capacitor, and if you want to take into account only the effect of QF, then you will have to apply a flat band voltage which is negative. And what is the value of this flat band voltage? That also we can determine. Since the charge is QF, okay, the voltage to be applied from the field and charge picture is VFB is equal to minus QF upon C naught. This is the simple parallel plate capacitor relation, that is the charge is equal to voltage into capacitance. Okay, so one can draw the charge and field picture here. It would be like this. So you have fixed charge positive on the semiconductor and equal negative charge on the gate. So this is the charge condition. Both are sheet charges. And now you have an electric field directed from this positive charge to negative charge. So this is your E versus X, and the value of the electric field is nothing but QF upon epsilon ox. You recall that when we wrote the electric field in oxide because of a certain silicon charge Qs, we wrote the oxide field as minus Qs by epsilon ox. So similarly here it is minus Qf by epsilon ox. Qf is this charge, area under this. So now area under this is the applied voltage. So following this approach you get flat band voltage equal to minus Qf by C naught. So the effect of a fixed charge is to shift the flat band voltage of an ideal MOS capacitor which is 0 to a negative value. Okay? So the flat band voltage is shifted from 0 to a negative value in a non-ideal MOS capacitor because of Qf. Now how do you take into account the effect of phi ms? To take into account the effect of phi ms, we will have to go to the energy band diagram. Now this is an important point that we arrive at here, that whenever you want to discuss a junction between dissimilar materials, okay, then you will have to use the energy band diagram. You cannot avoid the energy band diagram. If you recall, when we discussed the p-n junction, we said that when you have a p-n junction made in silicon, that is in the same material, one can do a great deal of analysis of this junction and derive the current voltage characteristics without the aid of energy band diagram. Although the energy band diagram approach gives you some additional insights, but without energy band diagram one can go quite far in understanding a p-n junction, which is a homojunction. Okay? So we can generally say, to understand a homojunction we can avoid the use of energy band diagram to a great extent, but while understanding a heterojunction or a junction between dissimilar materials, which is what a MOS junction is, because material here is different from the material here, and of course the material here is also different. Okay? So in such cases we need to use the energy band diagram to derive the effects of the contact potential or work function difference between the one material and another material. So next topic that we need to discuss in the context of non-ideal MOS capacitors is the energy band diagram. Now let us look at the energy band diagram when all the components of the MOS capacitor are isolated. That means you have the metal, then you have the oxide, and you have the semiconductor, and suppose these are all isolated. Now without any loss of generality, we will assume that the metal is also sufficiently thick. This is just to enable us to draw the energy band diagram, that is all. Now how do we draw the energy band diagram showing the bands in all the three? We must choose a reference. We know that the reference is normally the vacuum level. So we first draw E0. The various steps in the drawing of energy band diagram were given in the context of p-n junctions. We are following the same steps. Now in the metal you cannot have conduction or valence bands, you only have the Fermi level. So this is EFM, and this difference is normally referred to as the work function, the difference between the vacuum level and the Fermi level. So this is Q times phi m, where phi m is the work function in volts, E is energy. Energy band in the oxide is an insulator, it has a very wide band gap. So energy band diagram is something like this. This is the conduction and valence band. In fact, you can show it even larger. please remember that these three are isolated right now when we draw the band diagram. So there is no connection between them. So we are drawing the structure individually in each of these three. So this is EC and this is EV. Now we come to the semiconductor. In the semiconductor, you will first locate the EC and then EV. The band gap of semiconductor is obviously much less than that of the oxide. This EC is located at a distance given by Q times the electron affinity. Then this EV is located below EC, this is energy gap. Now since we are considering p-type silicon, your Fermi level will be below the intrinsic level, which is in the middle here. So this is the intrinsic level, so your Fermi level is somewhere here. So this is EF in the semiconductor. S stands for semiconductor. Now here we have shown a metal whose work function is more than the electron affinity in the semiconductor. It is not necessary that this should always be the case. You can have the Fermi level above this level here or below even valence band level. It depends on the metals. In analogy to the work function in metal, you can define a work function in semiconductor also. So that would be this difference, Q times phi S. Although the work function in semiconductor does not have that much real meaning as it has in a metal, because you can remove an electron from the Fermi level out of a metal. Okay, so when you remove an electron out of a metal, it is most likely to be at the Fermi level. Whereas when you remove an electron in a semiconductor, it is unlikely to be at the Fermi level, because Fermi level is in the forbidden gap and you do not have any allowed states in the forbidden gap for electrons. But still, it may help us in writing the equations. That is why we are introducing this work function in semiconductor. So Fermi level in the metal is above the Fermi level in the semiconductor, as we have drawn here. Now from this starting point, how do we proceed to the situation when you put all these three components together and join them by a wire? So that means now we draw the band diagram when it is like this. So we are joining them together. Please note that just if you join them together like this, the band diagram will be no different from this diagram. Okay? That is because since there is an insulator here, it prevents any interaction between the metal and the semiconductor. So no exchange of charges can happen. So even when these three components are stuck to each other, they are still as isolated as this case when they are separate. So when we talk of the energy band diagram of a MOS capacitor under equilibrium, it is necessary to note that the metal here is joined to the semiconductor here by a wire. Only then the MOS is said to be in equilibrium, that is all these three form a system, because in a system the various parts should be able to interact with each other, otherwise it is not a system at all. So in this case, what is the energy band diagram? We can start from here and we will note that since Fermi level is higher here than in this semiconductor, the electrons will tend to be transferred in this direction. So electrons are transferred from metal to semiconductor. Now please note that electrons are being transferred from metal to semiconductor because the Fermi level in metal is higher than that in semiconductor. One must not think that because metals are in higher concentration, the electrons are in higher concentration in metal than in semiconductor, therefore they are being transferred. Okay? So many times students have this misconception that because electrons concentration is higher in metal than in semiconductor, always you will have transfer of electrons from metal to semiconductor. This is not correct. For example, here in this case, if the Fermi level was below this Fermi level here, somewhere here like this, then even if this is a p-type semiconductor which has a very small number of electrons, when you join the metal and semiconductor by a wire, the electrons would get transferred from semiconductor to metal, okay, because the Fermi level here is higher than here. So it is a Fermi level difference that decides, because Fermi level represents the average energy of electrons, and electrons always move from regions of higher energy to regions of lower energy, just as water goes from a point which is at a greater height to a point which is at a lower height. Okay? So even if you have a container like this which is small and you have a big container here at a lower height than this, then when you join these two by a tube, the water will flow from this to this, even though the container is small, because it is at a greater height than here. So it is the height that decides the transfer of water. Similarly, here it is the Fermi level that decides the transfer of electrons, direction of transfer of electrons. Now, how are the electrons transferred? Well, even though the electrons have been shown to be transferred like this, it does not mean that they are going through the oxide, because the oxide would not allow any electrons. So basically this transfer is taking place through the wire here. So this is how the electrons are transferred. Now after the transfer takes place and equilibrium is established, you know that both these Fermi levels should be aligned, because in equilibrium the Fermi level should be a constant. Therefore the band diagram would look something like this. You should draw a constant Fermi level. Now please note that we are not drawing a Fermi level in the oxide, because oxide is an insulator. Really speaking, there is no Fermi level. Okay, having drawn the Fermi level, now you identify a space charge region. You are following the same sequence of steps which we followed for p-n junction. Now we ignore the width of the space charge region in the metal, because that is really very thin. Now here you see that if electrons are transferred here, they would recombine with holes on the p side, and in effect what you are having is therefore depletion of holes. So you are creating a depletion layer. Therefore the extent of this region would be much more than a sheet charge, because you are having a depletion layer. So hole concentration is going to decrease as compared to bulk. Now you draw the energy band diagram in the bulk. In the bulk, it is, bulk means away from the space charge region. So this is what is the energy band diagram in semiconductor, away from the bulk. And now you must complete the picture. The whole concentration is reducing as you come to the surface. So it is something like this. Okay, and you can complete the picture for vacuum level. This is E naught, this is EC, this is EV, and this is EF. So something like this. This is your E naught. Now what about the vacuum level in the metal? Vacuum level in the metal will be at the same distance from the Fermi level as it was here. Now one way of understanding how this bending occurs in the energy band diagram is to build up this diagram as follows. So here you find that the electrons will move into the semiconductor, and therefore the Fermi level here will come down. Okay, so we assume that the Fermi level is coming down here, and it is trying to it is aligning with this metal. Actually this is coming down and that is going up, but for simplicity we will take this as the reference and then we will say this is coming down. So along with this the E naught also will come down. So you have E naught here, somewhere here. So that is how the diagram looks. Note that we have not drawn the diagram in the oxide. You can draw it in the oxide also, okay, but that adds to the complexity, and for a first course we need not bother about this diagram in the oxide. In fact, whatever effects we are going to discuss, those effects do not depend on the energy band diagram in the oxide. They depend only on the diagram in the metal and semiconductor. So this is the picture under equilibrium. So you see what has happened is, because of the contact potential, even when the applied voltage is 0, you have a charge in the semiconductor. In this case it is a negative charge. So this is the effect of the contact potential, that even when the applied voltage is 0, you have a charge in the semiconductor because of charge transfer between metal and semiconductor originating from difference in the Fermi levels in the two regions. So that is the effect of non-ideality. So which means if you want to create a zero charge condition in the semiconductor, now you will have to apply a voltage to the gate. In other words, the flat band voltage will not be 0. That is the effect of the work function difference. Now how much voltage should we apply so that the charge conditions are 0? When you have 0 charge here, the energy band diagram would be the same as this. That is a flat band condition. Okay. So to achieve this flat band condition, you will have to remove the negative charges which are there in p type. So from here we start and we have to remove the charges which are there in p type. So to remove the charges in negative charges in p type semiconductor, you must apply a negative voltage to the metal. So which means you must lift this Fermi level up, because increasing energies here, these are electronic energies. So when a Fermi level moves up, it means that you are applying a negative voltage. So in order to get flat band condition, what you will have to do is you will have to introduce a power supply here with a negative polarity, because in this particular case you have negative charge in the semiconductor. So once you do that, provided the power supplies of a proper magnitude, we will shortly see what the magnitude is, all these negative charges will be repelled. So that is interesting, that you have 0 charge condition in the metal for a given applied voltage. So this is the flat band voltage. Now the difference in the Fermi levels here, so this is the condition now for V equal to VFB. So the band diagram for V equal to VFB is the same as the band diagram when the three regions are isolated or not joined by a wire. Then this difference between the Fermi levels indicates the amount of applied voltage, because under equilibrium the Fermi levels are aligned. This is the flat band voltage, or the voltage you have to apply to the gate. Now evidently this voltage is equal to the difference in the work function of the semiconductor and the metal. Okay. So we can therefore say that the effect of the work function difference phi ms is that the flat band voltage equal to phi ms should be applied to create flat band conditions. So we write VFB effect of phi ms is to create a flat band voltage equal to phi ms. phi ms is nothing but phi m minus phi s. Okay. So please note, I repeat from here that this voltage is equal to is the difference of these two, okay, but in magnitude it is negative. So this voltage is obtained as this minus this. Now we have already seen that the effect of QF was to create a flat band voltage equal to minus QF by C naught. So this was assuming that there was no phi ms. So effect of QF when phi ms is 0 is this, and effect of phi ms when QF is 0, so we considered no QF in this case, is this. So whenever you want to understand the effect of two parameters, you must understand them one at a time. That is what we are doing here, okay. So from these two we can easily get the effect of phi ms and QF as follows: in presence of phi ms and QF, you can simply write the flat band voltage is equal to the superposition of these two, that is phi ms minus QF by C naught. So we are simply summing up these two to get the effect when both phi ms and QF are present, okay. We can summarize all this discussion on the effect of QF and phi ms in a non-ideal capacitor as follows. This is the picture we had for the ideal capacitor. So zero charge condition in the silicon at 0 volts, and then threshold at a voltage given by this formula. Now the zero charge condition occurs at flat band voltage. In other words, if you simply change this V to V minus VFB, then this whole picture is valid. Same thing you do here also. The charge was 0 for voltage equal to 0, but now the charge is 0 when voltage is equal to VFB. In other words, if you change this to V minus VFB, this whole diagram becomes valid and it becomes applicable to a real capacitor. So we can therefore say that the effect of non-idealities of QF and phi ms is to simply change the zero charge condition to flat band voltage and the threshold voltage to the following formula. So the threshold voltage is now given by Vt is equal to the threshold corresponding to ideal capacitor plus VFB, right, because V minus VFB is this, okay. So therefore V is VFB plus this, so Vt of a real capacitor is Vt of an ideal capacitor plus VFB. We shall continue the discussion in the next class.